Thanks, Juan, for the introduction. Yeah. A second. All right, that looks good. Okay, yeah. Today I would like to present a bit the architecture of our DTN protocol implementation, which is µD3TN, written as µD3TN, and yeah, how we got there basically. There is also the paper that we handed in about that, which gives a lot more detail, but I would like to briefly go through the highlights of that in my presentation. All right, let's briefly start with the basic facts about it. So what is µD3TN? It was formerly called µPCN. It's an open source bundle protocol implementation, implementing bundle protocol version 6 and 7, written in C. We are targeting POSIX. We are supporting like Linux, BSD, Mac OS, and µD3TN is also portable to microcontrollers. We are targeting to have a very low resource usage and use few dependencies. And yeah, right now in 2024, it has been in development for about 10 years. The basic objective of our paper now was to document our design decisions over the course of those 10 years and the reasoning behind them as well, to share our experience with the community and also to give some input to discussions to improve the architecture of DTN protocol implementations, of course also including ours. So yeah, maybe we'll also have a very nice discussion about the architectures later in the afternoon in the panel discussion. Let's start with a brief insight into the history of µPCN as it started in 2014. In the beginning, we had planned to evaluate a concept called the ring road networking concept, which is like an approach to establish a very low-cost data carrying network with only a few low Earth orbit satellites. And this should be tested on a CubeSat mission at that point in time by the University of Dresden, where we were working at that point in time. And this CubeSat mission should use a microcontroller, an STM32F4 microcontroller, and FreeRTOS as operating system. So we only had very basic platform support available, only basic libc, no POSIX API, and also very basic hardware, as you can see on the bottom. This was our evaluation board that we used, the STM32F4 Discovery. The basic architecture was using the tasks provided by FreeRTOS, so kind of like threads in normal operating systems that interact through message passing queues. And this very basic architecture is still like the basis of µD3TN at this point in time, but obviously it looks a bit more enhanced, but we will see that later on. So starting from that initial draft implementation for this mission, which unfortunately then was not working out for us, but from the mission side, not from the software side, we were driving the development further, enhancing µD3TN with many more features, starting with, for example, a port to the POSIX operating system API, so that we could test it not only on a microcontroller board, but also on our development machines, which was really speeding up further developments there. And then we integrated things like the bundled protocol version 7 draft. At that point in time, I think it was draft version 10 or so. And while the BP version 7 was evolving in IETF, we aimed to keep up with the changes in the draft and implemented them, and also gave some feedback in the IETF meetings. We also implemented then things like an interface for modular convergence layer adapters, like on the bottom side of our bond protocol agent, and we also implemented an application interface called the application agent protocol. I have some more details on that later on. And after that, we performed testing, and based on the tests, we did refactoring. We did some further enhancements. We had quite some findings from those tests that resulted in further enhancements to the implementation. And further features include the implementation of the bundle encapsulation CLA. We explored a port to the Rust programming language. We are still exploring that. It's on our roadmap to provide this at some point, but currently it's like a very early prototype still. And now we are working on enhancing the forwarding subsystem of micro DTN with a more generic approach through a generic forwarding interface and a extended application agent protocol that integrates with that. I will get to that later on. Also, persistent storage is integrated. I also have a dedicated slide on that. Overall, the general design goals underlying this development are still to keep it a minimal BP stack, have very few dependencies, be extensible, and also be highly adaptable through well-defined interfaces. So we always keep trying to have very clean interfaces, for example, for CLAs, for the applications, and also for the forwarding algorithms. And the aim of this is also to make it a simple, easy to use implementation for research on the one hand side and productive networks on the other. I would also like to give an overview of how we developed this before getting into more architectural details. I would say the setup for developing micro DTN and testing it is quite usual. We are using Git and GitLab as hosting platform. We have a quite large set of CI tests, including unit integration and interoperability tests. We have custom CI runners, so we are not only using this cloud runners provided by GitLab, but we have like a test rack shown here, which includes our targeted platforms. We have like Linux runners, ARM64 CPUs. We have FreeBSD and Mac OS with an M2 CPU here. This Mac Mini. And so testing on a wide variety of platforms that we want to support. When developing new features for microDTN, we always consider concrete application scenarios. So like in the beginning, I talked about this ring road network scenario for which we developed the first version of the software. And so always we try to have a very concrete focus for new features that we can also develop tests for those specific scenarios that we can validate that the software works in there, and that in the future there will be no regressions preventing it to work in those scenarios. We try to perform early and extensive testing always in as realistic setup as possible. So focus on integration, interoperability tests, and if possible, field tests. I briefly mentioned testing on a low Earth orbit satellite. It was ESA's OPSAT, which we used in 2020 and 2021 for testing. We also performed some testing in deploying a small DTN in the field with some drones. I have a dedicated slide on that as well. And so we always try to do some practical testing as well to really have have an extensive network setup integrated and to really see how it works in practice. And yeah, as I said, interoperability testing is also one of our focus points. We performed some interoperability tests together with Spatiam, for example. We integrated ION, we integrated DTN and DTN7 in our CI pipelines for basic interoperability tests. And those are run basically against any change in micro DTN so that we can really see that nothing breaks in there. So yeah, talking about field tests, we performed quite some integration into some prototypical hardware to see whether it really works in the field as well. The first test was in 2019. We had a small research project funded by ESA Business Applications called ColdSun. There we developed a buoy prototype for connecting a underwater sensor network to the internet using DTN technology. The uplink in that case was using OrbCom, so nothing disruption or maybe a bit delay tolerant, but quite off the shelf. The disruption tolerant part in this case was connecting to the underwater sensors, which were using small acoustic modems and were moving underwater the buoy. So only at some times there was connectivity to it, and they were delivering sensor data like temperature readings, pressure readings, and so on. This example through micro DTN and to a monitoring server on the internet. I briefly mentioned the OPSAT testing as well. We deployed micro DTN on this LEO satellite in an experiment in 2020, and also did an interoperability test in the ground infrastructure against ION, in which Spatiam supported us. Another test was 2 years ago in a project we call Red Mars. There we emulated a small Mars to Earth network on Earth to show that micro DTN can also deal with ad hoc discovery and be integrated at the same point in time into a space network which has like a continuous connectivity based on a contact plan. And this was demonstrated using 2 UAVs, so 2 drones that were deployed on a field here, near Dresden in Germany. The last test shown on that slide was for the Lunar Ice Cube satellite, which was also an interoperability test, including a larger variety of DTN protocol implementations. And there, micro DTN's job was to provide data delivered from the network that was spun up by Morehead State University, NASA, and ESA to the internet, and basically also provide a web access to that data. Unfortunately, the Lunar Ice Cube failed to deploy at some point. However, we were performing an emulation experiment based on real data, and were able to show their interoperability also with the other implementations. In the future, we plan to focus on a more broader scope of topics in our tests, like evaluating the performance of micro DTN, performing more interoperability tests, more extended interoperability tests that use more features of the DTN protocol implementations as well, and increase also the automation of the tests, like the configuration of the DTN protocol implementations, management, integrate management approaches, security is also a topic that we want to tackle here. To show some more details, some more pictures on that one test with the drones we performed. As you see, we did this on a field here to emulate a link to two autonomous drones that could be deployed on Mars, for example. We were emulating the satellite link using also ESA's OPSAT in that case, and included specifically some novel features of µD3TN and some applications we developed around that to, for example, autonomously dispatch the drones based on destination node identifiers of the bundles. So that was one feature we integrated for that prototypically, where we monitored incoming bundles, and based on the destination that was specified in the bundle, for example, a specific like the second drone that we were operating there, we could specify GPS coordinates for the drone to fly to, and then it came in contact with the second drone and performed ad hoc discovery and sent the bundles further there. But so much about the overall development and testing approach. In the second part of this presentation, I would like to highlight some notable design decisions we derived also from the results or from the experience of those tests and implemented in µD3TN. One of them is to make µD3TN stackable, I would say, via the bundle-in-bundle encapsulation feature. This means that we can set up µD3TN instances like above each other recursively up to an arbitrary depth. So we have our application interface that is called the application agent protocol. It can be accessed through POSIX IPC sockets and TCP sockets. And we have the BIPE CLA that connects to such a socket. And so we can, basically set up arbitrary networks stacked on top of each other that basically don't need to know about the characteristics of the other the underlying network. So this, of course, can be used to improve scalability, to reduce the scope of things like the routing tables, contact plans, and so on, and also makes us be able to support heterogeneous networks, like having subnetworks that just perform next hop forwarding, opportunistic routing, whatever, and on the other hand, integrate them with networks that rely on contact plans and know all the nodes and the contacts that may occur between them. I also briefly mentioned that we have a generic bundle forwarding interface. This is a more recent development even. This was one finding from the project where we deployed those drones in the field test. We found that it is very valuable to have a generic interface to attach different forwarding algorithms. So, for example, to have like opportunistic forwarding and deterministic forwarding, and have them easily exchangeable in configuration when launching the DTN protocol agent. This allows also fast and easy prototyping. It allows integration of stuff like dispatching the drones autonomously, monitoring, and so on. And this is realized basically by dividing up the bundle protocol agent into two parts, which is this and that. So we have like the bundle protocol agent core, as we call it, that receives the bundles, performs all the basic BP processing steps, and then emits events to this so-called bundle dispatcher module, BDM, which then decides what to do with the bundle, basically. And it can then specify actions like forward the bundle to a specific node, drop bundle, store it, whatever. And this makes it very flexible for us to adapt to different network scenarios. This interface is combined together with our application interface into a new version of our application agent protocol, which is now available also in the current development tree of µD3TN, called application agent protocol version 2.0. And this integrates an interface for, on the one hand, sending and receiving bundles, but also for controlling the links that µD3TN establishes, and to control the bundle forwarding decisions. Of course, you don't want any application on the system that can connect to your BPA to perform such actions, so you have to somehow secure that. So this is why we have a very simple approach to authentication and authorization there, using just a shared secret. So we have like a privileged secret that applications have to specify to perform things like link management and management of forwarding decisions. And we also use this for securing bundle endpoints where multiple applications may register. So you might have like multiple applications registering under the same endpoint. For example, one wants to send bundles, one wants to receive bundles under that endpoint. In this case, you need to specify the same value for the shared secret. And so you can even have like two application instances receiving bundles under the same endpoint, and three application instances sending bundles under that endpoint, which is secured using that mechanism. It's provided via POSIX IPC sockets as the previous version, and uses protobuf for the on-wire representation, so that we also have a clean declarative specification of the interface. Another design decision we were making was that we don't want to have a persistent state inside our BPA for reducing complexity, to really be very minimal. And for this, we implemented storage as a specific kind of CLA. That might sound a bit interesting, but all in all, in the end, it's like the storage in our case, it's just a delegation of storing the bundle to another node, and we are implementing a special CLA that represents a minimal bundle node that just stores or recalls bundle from storage. We have this implemented in the first version, also in the development tree that's available now. And this is using SQLite, so we don't have to care about like syncing files and so on, and supports file databases and in-memory usage as the previous version of µD3TN did. This is also secured using the AAP 2.0 shared secret mechanism, which sets an authorization flag in a bundle, because of course you don't want to let any application control your storage on the node. All right. Just before I run out of time, a brief view of the overall architecture that results from that. Basically, µD3TN in the end is like just a basic bundle multiplexer, you could say, which is like it receives bundles from CLAs through a queue and then just decides where to forward them. This could be storage, this could be another node that is directly connected, or of course the bundle could be dropped as well. And the interface that we have on top with our bundle protocol, with our bundle dispatch modules, makes it basically software defined. We can attach different implementations there. We can exchange them even at runtime if we want, and control the operation of this bundle protocol agent. So to give an outlook into to some current work we are performing, we have just finished a master thesis with one of our working students, which built a performance test bed using some realistic hardware, which can compare different bundle protocol implementations regarding things like good put, processing delay, resource usage, and so on. Currently, we have integrated µD3TN and ion. We are now working on integrating HDTN in the next step. And of course, we want to publish this. There is a very early draft available on the internet, but we also plan to write a paper on that and do a real public release with some good documentation of first results as well soon. To summarize, basically we are building a software-defined DTN data plane with µD3TN that's very adaptable and flexible. And in the next step, we are making it ready for productive commercial use. We are just working on stability and performance optimizations right now. We are working on the further performance testing, as I showed, that will make it more efficient, more stable to use. And we are also planning to provide more tooling, more forwarding algorithms, CLIs, and so on, because that's still quite minimal at the moment. But documentation and additional services are also, of course, one focus point, so that we have really the whole package of a commercially usable DTN protocol implementation at some point. And that should be it. Thanks for your attention. Happy to receive a question.
Time for maybe one or two quick questions. So yes, right on. Yes.
I was just curious if µD3TN and your team have ever encountered a use case where you've wanted to use a microcontroller that doesn't have Ethernet, but maybe has serial port, CAN bus, or SPI, or I2C. I was just wondering if you've ever come across that challenge.
Actually, the first version that I was showing, this microcontroller didn't have any Ethernet or socket support. Okay. For testing, we were using like the serial interface. Okay. It was planned to integrate this, I think, with an SPI interface. However, this was then cancelled because the mission was restructured and we were not allowed to integrate it anymore. So in the end, we decided to focus on systems that have like a socket interface available for now. But we have a platform abstraction that could be made to integrate also with things like a serial port or SPI if we want. But at the moment, it's not really something we focus on.
Maybe we can chat after.
Sure, of course.
Yeah, so I also invite to chat afterwards with Felix because we are a little bit over time now. So we thank you one more, Felix.